We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Before I switch over to WRC BIM, let me tell you what we do in the case of singly RC BIM. So in singly RC BIM, we provide reinforcement at bottom of the beam, means in the tension zone of the beam, and at the top, means in the compression zone, we do not provide the reinforcement except 2 numbers of anchor bar. While in the case of WRC beam, we provide reinforcement in tension zone as well as in compression zone. Means in both the zone we provide reinforcement. So question automatically arises in our mind, why we provide reinforcement in the compression zone? Which are those situations in which we have to provide reinforcement in the compression zone, right? So let me explain this by giving an example. Say width of the beam is 300 mm, effective depth of the beam is 600 mm, effective cover of the beam is 50 mm, reinforcement provided is 2 number 20 dia, so area comes 1256 mm square, and the concrete grade used is N20 and the steel grade is Fe415. Now let me draw the cross section of the beam for this data. B is 300 mm and at the bottom 4 number 20 mm dia bars are provided. This is ASD. This is neutral axis, and bottom of the beam there will be tension and the top of the beam there will be compression. This is effective depth 600 mm. Cross section of singly RC beam. Now for Fe415 grade steel, the MU lim means limiting moment of resistance is 0.138 FCK BD square. If we put all the values, we get the answer 0.138 into 20 into 300 into 600 square, 298 into 10 to 6 Newton into mm means 298 kilonewton into meter. Okay. Now let me explain what is MU lim. MU lim means maximum moment resisting capacity of the beam. Okay. If singly RC beam having width 300 mm, effective depth 600 mm, and the materials used are concrete is N20 and the steel is Fe415. So with this dimension and these properties of materials, the maximum moment resisting capacity of singly RC beam is 298 kilonewton into meter. Means this beam can resist maximum moment of 298 kilonewton into meter. Now, if due to some reason heavy load comes on the beam, and due to that heavy load, moment produced in the beam is somewhere about mu 400 kilonewton into meter. So what happens here? Applied moment is more than the moment resisting capacity of the beam. Means mu is greater than mu limit. So in this case, if we do not care of the beam, obviously beam will fail. So in this case, we have to increase the moment resisting capacity of the beam. For increasing moment resisting capacity of the beam, we have basically three options. The first one is to use higher grade of concrete. The first one is using higher grade of concrete, we can increase the moment resisting capacity of the beam. Means instead of M20 grade of concrete, if we use M25, M30, M40, we can increase the moment resisting capacity of the beam. Let's take the example. Say, instead of M20, if we use M30, what happens? Mu lim, means equation of mu lim will remain same, 0.138 FCK BD square equal to 138 FCK is 30, B 300 and D 600 square. So what happens here? 0.138 into 30 into 300 into 600 square. So it comes 447.12 into 10⁻⁶ Newton into mm. 447 kilonewton into meter. See, if we use M30 grade concrete instead of M20 grade concrete, we can increase the moment carrying capacity of the beam from 298 kilonewton into meter to 447 kilonewton into meter, and the applied moment is 400 kilonewton into meter. So in this case, our beam won't fail. Now, the second option is to increase depth of the beam. To increase depth of the beam means if we increase depth of the beam from 600 mm to 700 or 800 mm, we can also increase the moment resisting capacity of the beam. Say, let's take the example D equal to 600 mm. Instead of 600 mm, let us take 700 mm. So the equation of mu lim will remain same, 0.138 FCK BD square. 0.138 FCK is 20, B is 300 and D is 700 mm. When we calculate this, 300 into 700 square, it comes 405.72 into 10⁻⁶ Newton into mm is equal to 405.72 kilonewton into meter. See, if we increase the depth from 600 mm to 700 mm, we can increase the moment resisting capacity of the beam from 298 kilonewton into meter to 405.72 kilonewton into meter, and the applied moments is 400 kilonewton into meter. So in this case also beam won't fail. Now the third case is to provide reinforcement in compression zone. Okay, to provide reinforcement in compression zone means if we provide reinforcement in compression zone, we can also increase the moment resisting capacity of the beam. Why it happens? Because we know steel is strong in tension as well as in compression. Means the same strength steel will give in tension as well as in compression. So naturally, if we use reinforcement in compression zone, its compressive strength will increase, and in this way moment resisting capacity of the beam will increase. So among these three methods, to increase the higher grade of, to use the higher grade of concrete, to increase the depth of the beam, and to provide the reinforcement in compression zone, means among these three methods, if we use this third one to increase the moment resisting capacity of the beam, that concept is called WRC beam. Means if I have to define the WRC beam, then I would that it when applied moment is more than limiting moment of resistance of the singly RC beam, moment resisting capacity of the beam is increased by providing reinforcement in the compression zone. This type of beam is called the WRC beam. So now let's see the concept of WRC beam by okay. So first let's draw the cross section of the WRC beam. This is width of the beam in tension zone. Say 4 numbers of steel bars are used. This is called AST. And in compression zone, 3 numbers steel bars are used. This is called ASC. And this is effective depth. This is called effective cover in tension zone. And this is called D dash, effective cover in compression zone. This is the neutral axis. Bottom of the neutral axis will be in tension and the top of the neutral axis will be in compression. This is cross section of WRC beam, right? So if I divide this WRC beam in 2 parts, then how it will look? So this is the singly RC beam, means in limiting section, singly RC limiting section beam. This is called AST1. And in compression zone, it is assumed no steel is there, only concrete is there. So here only concrete, no steel. This is assume that in singly RC limiting section of the beam, in tension zone, AST1 is provided, and in the compression zone, only concrete is there, no steel is there, right? Plus, so let me explain in some another way. As I have already explained, for 400 kilonewton into meter, we have designed the WRC beam, means we have designed the WRC beam. In our case, we have designed the WRC beam for the moment of 400 kilonewton into meter. Now, if we design the singly RC beam at limiting section, the capacity of this singly RC beam is 298 kilonewton into meter, right? So, additional 400 minus 298 means 102. 400 minus 298, 102 kilonewton into meter moment is remaining. So for this 102 kilonewton into meter, one additional section is provided, which is called auxiliary section, or you can say additional section. So in this section, see, in WRC beam definition, what we have described, a additional moment resisting capacity, means the resisting capacity of the beam is increased by providing the reinforcement in the compression zone. But in this case, means for auxiliary section, means for this additional 102 kilonewton into meter, we provide reinforcement in compression zone as well as in tension zone. Yes. So this is called AST2, means for 102 kilonewton into meter, we provide reinforcement in compression zone, which is called ESC, and in tension zone, we also provide the reinforcement, which is called the AST2. And here, means in auxiliary section, in compression zone, it is assumed that there will be no concrete, only steel. Now, if we combine this plus this, it will become this, right? So this is all about the concept of WRC beam. In addition to this, let me tell you one more thing: reversal of stresses. Reversal of stresses, right? Means when there are reversal of stresses, in that case we can't use the singly RC beam. Means in reversal of stresses we must use the WRC beam. So why? Let me tell you first what is reversal of stresses. Generally, when we design the beam, we assume that bottom of the beam there will be tension and the top of the beam there will be compression, right? This is the basic. Now, due to earthquake or due to lateral load, in the case of earthquake or lateral load, what happens? There may be compressive stresses developed at the bottom of the beam and tensile stresses develop in the top of the beam. Yes, there are chances that what we have assumed, its opposite happens. Means bottom, we have assumed that at the bottom of the beam there will be tension, but due to earthquake load or lateral load, there are chances, there may be possible that bottom of the beam compression will be there and the top of the beam tension will be there. So if if our beam is singly RC beam, so we know that in singly RC beam only only at tension zone reinforcement are provided. So when earthquake load is come or lateral load is come, what happens at bottom? Compression stresses are developed and at top tensile stresses are developed. So in bottom reinforcements are there. So due to compressive stresses, there will be no damage. Why? Because steel are strong in tension as well as in compression. But what about at top of the beam? In singly RC beam, at the top, there is only concrete, right? There is no reinforcement. And we know that concrete is very weak in tension, which is tensile strength of concrete is 0.7 under root FCK. And if top of the beam tensile stresses are developed, so there may be a chances to damage the beam at the top of the beam. While in the WRC beam, bottom as well as top means in both the cases, in both the area, in both the cases, reinforcements are there. So if due to reversal of stresses, this may change that compression stresses are developed at the bottom of the beam and tensile stresses are developed at top of the beam. No matter where compression and where tensile stresses are developed, WRC beam will be capable to resist both types of stresses. So this is called reversal of stresses. Reversal of stresses is whatever we have designed, it will oppose, right? Opposite nature type of stresses will develop. So in this case, WRC beam must be designed. Okay. So this is all about the concept of WRC beam. So I stop here. Thank you.